Okay, so we left off last segment. Um, we found that radius of curvature, and we used that assuming that that was a circular arc that the beam deformed into to get to calculate an exact deflection. Now, a couple of things there. One, that's kind of a lengthy process, and two, the beam won't necessarily deform in a perfectly circular arc. So there are some formulas that have been developed that are a little bit more exact, I should say, in finding that deflection. These are found on page 406 and 407 in your textbook. And it basically defines different loading conditions. So we'll take a look here. If we have a distributed load on a beam, and we're going to call that distributed load omega PLF. And the span of the beam is L. The deflection, and the symbol that's usually used for deflection is delta, a little triangle. So that deflection, delta, the max just means this is the maximum possible deflection due to this loading condition, is 5 times omega times the span or the length to the fourth power over 384 times the elastic modulus times the moment of inertia for the beam's cross section. Okay, there's a lot of stuff there. Let's say that this is a steel I-beam. And the steel I-beam, well, let's go to our tables and see what we find here quick. Back of the book. Let's do a wide flange. 1443. What is its moment of inertia? 428 is given as its moment of inertia. Forgot what I listed there as what beam I was using. So it's a W1443. Okay. It's a W1443. I is 428. Now that's steel, so we need to know our modulus of elasticity. For structural steel, we can go back to our tables. There's one on page 273, but the more useful one is on page 278. For metals, A36 structural steel modulus of elasticity is 29 million. So let's say that this beam is 16 feet long and omega is 400 PLF. So then the deflection here is 5 times 400 times 16 to the power of 4 over 384 times 29 million times 428. Well, this was mostly all figured out before they had television. So they basically, that was their entertainment. Let's figure out how much a beam deflects. Let's face it, if they had Nintendo back then, this never would have happened. So 5 times 400 times 16 to the power of 4 divided by, parentheses, 384 times 29 million times 428. Ta-da! So that's scientific notation. That's saying 2.75 times 10 to the negative fifth.
Wait, how are you? Oh, in the calculator. Okay, never mind.
Yep. So that's negative 5 means you move that decimal point over 5 spots. That's 0.0000275 inches. Oops. I gotta be careful. Length. Do I need to convert my length into inches? Yes, I do. Sorry. I gotta change that. Do I? Nope, it's saying I can leave it in feet. Okay, I was just making sure. Well, I'm not seeing it now. Here, we're gonna pause while I sit here silently. And so let's go back and change that. I'm pretty sure we do have to have that in inches for that. This will be 5 times 400 times 16 times 12, and that's going to be to the power of 4. Over the 384 times 29 million times 428. So let's try that. 5 times 400 times 16 times 12 to the power of 4 divided by 384 times 29 million times 428. That's better, 0.57. That's about what I was expecting out of that. So 0.57 inches is what we are going to flex. Now, is that allowable? Well, we need to check. This was a 16-foot span. So it's going to be 16 times 12. We didn't really give an application. Let's assume this is an L over 360 application. So 16 times 12 converts that span into inches. Divided by 360, 0.53. So we're really close. We're a little bit more than what we should be on that. Now we did an L over 360 application. Chances are if you're using a steel I-beam, it's an L over 240 application. Usually steel I-beams are in the floor. So I mean, well, let's take a look at another example. Let's look at a concentrated load, a point load for the second formula they give there. If we have a simply supported beam with a single concentrated load at the mid-span, we call that concentrated load P. The span or length is L. The maximum value of delta would be P times L to the third over 48 times the elastic modulus times the moment of inertia. Let's assume this is a 12-foot beam supporting a 2,000-pound concentrated load, and that it is 3 by 12 wood with elastic modulus. I'm just going to look just to make sure I'm getting the right number. Wood is usually 1.7 or so. Yeah, it looks like we can stick a 1.7 or 1.6 for elastic modulus. We'll go E of 1.6 million. So you define our moment of inertia, which will be the 3 times 12 to the third over 12, which is 432 inches to the fourth. So anyway, we'll set this up. We have P of 2,000 pounds times L, well, it's 12 feet times 12 to make it into inches to the third power, over 48 times 1,600,000 times 432. So 2,000 times 144 to the power of 3 divided by 48 times 1,600,000 times 432 equals 0.18 inches. Now it's a 144-inch span, even if we go with the strictest of conditions. The most restrictive would be an L over 480. 144 divided by 480, we're still going to be well over 0.3. So 0.18 deflection is well under a 0.3 limit, even in the most strict of deflection restrictions. Chances are that's an L over 240, which would allow us up to 0.6 of an inch. We're only getting 0.18 of an inch. So we're well under our allowable deflection there. Then they go on and they give deflections for if you have 2 equally spaced concentrated loads or 3 equally spaced concentrated loads. I'm not going to do each of those separately. The formulas are there. You just have to plug in the numbers. But what I am going to do is an example like this. So we are going to have a 24-foot beam. That is, let's say that this is 200 PLF. And there are 2 equally spaced concentrated loads, each of 1,000 pounds. When it comes to deflection, it is truly additive. So what we can do is this. We can find the deflection for the 200 PLF 24-foot span. And then we can find the deflection for the 1,000-pound concentrated loads, spaced 8 feet apart. Then we can add the 2 deflections together. So we need to know a little bit about our beam. What are we using for a beam? This is 24 feet, so we're going to use a 4-inch by 24-inch wooden beam. Elastic modulus, 1,600,000. Moment of inertia is 4 times 24 to the third over 12. Which is 4608. So our deflection here for the concentrated load, delta is going to be 5 times omega, which is 200, times L, which will be 24 times 12 to the 4th power, over 384 times E, which is 1,600,000, times I, 4608. So 5 times 200 times 24 times 12 to the 4th, divided by 384 times 1,600,000 times 4,608. 2.43 inches. I'm going to assume this is a fourth. This is an L over 240 application here. So we got 2.43 inches of deflection just from the distributed load. Now we need to do the concentrated loads. We're going down to equation C down there, the third one in the table. 2 equally spaced concentrated loads. And that is, I'm going to use the second version of the formula. It's P, which is each single load is 1,000 pounds, times L, so 24 times 12 to the third power, over 28.2 times 1.6 million times 4608. So let's do that. 1,000 times 24 times 12 to the third divided by 28.2 times 1,600,000 times 4608. 0.115. So we have 2.43 plus 0.12 around it too. That's 2.55 inches of deflection we're going to get off of that. So I want you guys to try one. We're going to do a simply supported beam. We're going to go a 14-foot span. (120 PLF) with a single 1,200-pound concentrated load at center span. I'll let you guys try that. See what good question. Cross section. We're going to do a 4-inch by 18-inch rectangular beam. Elastic modulus will be 1,600,000. So you guys will have to find I. So let's see what we got. First of all, our span 14 times 12 is 168 inches. What'd you get for the moment of inertia? Not everybody at once. 1944. Okay, so for the distributed load, we have 5 times 120 times, oh, I know why. I see what we gotta do different here. I'm gonna do a little change here. Something just hit me. Something in that formula, I realize you guys wouldn't have caught this, but so the answer you guys probably got on your own is wrong here. I just remembered where the formula came from, so now I understand why the book did what it did. This top term, 5WL to the fourth, that's just compressed for the formula. It really is this, 5 times WL times L to the third. Why do I break it up that way? Because WL is the load, 120 pounds per foot times 14 feet. So when we do this, yes, the length is 168 inches, but that's only for the third power. So this is going to be 5 times the 120 PLF times 14 feet times, then we do the 14 times 12, or the 168 inches to the third power instead of the fourth power. Okay, does everybody see where that came from, why I made that adjustment? Over 384 times 1,600,000 times 1944. Yeah, but only to the third power. This gets broken up into L times L to the third, and the L to the third power gets changed to the inches, but the first L stays in feet. because that first L multiplies the omega to give you the actual load from the distributed load.
So all the other ones we did were wrong.
The first couple we did were wrong, yes. We'll finish this example, we'll call it a day, and we'll come back on Thursday and we'll go over it again a little bit, since I messed up. So 5 times 120. In fact, you know what? Since I made that correction, let's leave this example. This example can be your homework, and we'll go over it on Thursday, and we'll go over more of this on Thursday. How's that sound? So this one problem is your homework with this clarification being made. That'll be my consolation to you for